Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And in this module we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process over the CPU, right? So within the second module, we are currently on the second topic, which is process address space. And here through a series of videos, we are trying to understand what is the process address space, right? So every process has its associated address space, right? Which is a collection of addresses. And this address space allows the or enables the process to organize this code and data in a certain way. And we have talked about this that the address space has four major sections. Till now we have covered the code section, stack section, and the data section. So the last section that remains to be covered is the heap section. So in this video, let us now study what is the heap section and why do we use it. So without further ado, let's get started. So this is the process address space, right? We have already discussed about the code, data, and stack section. Let me quickly recall what all we have studied till now. So we know that the code section is used to store the instructions of the program. So when you compile your source code, you get a program, which is a bundle of data as well as instructions. So the instructions go to the code section, and the majority of data goes into the this data section. This includes objects like static variables, global variables, constant values, right? All of this are allocated in a static way. That is their static allocated memory, right? They last throughout the execution of the program, right? So we have talked about the data section in great detail in the previous video. And finally, we have also talked about the stack section. So the stack section is a dedicated section in the address space that is used for the execution of the functions. So for every function call, a stack frame is pushed onto the stack, right? And in this way, the stack section enables the support of execution of functions, right? And it not only helps to execute the functions, it also stores the data that is local to the function body, that is the local variables, the arguments, return addresses, all of that is also stored onto the stack. And finally, now we come to the heap section. So in this video, we are going to cover about the heap section. So why do we have the heap section? Basically, the heap section is a pool of memory that is reserved for dynamic memory allocations, right? So we have talked about what is static and what is dynamic memory allocation in an earlier video and what are the differences about them in great detail, right? So dynamic memory allocation, basically when the size of the memory that we are talking about, it can vary during the program execution, then we say that it is dynamic in nature, right? It can grow or it can shrink, right? So this is called dynamic memory. Some examples of dynamically allocated data structures include linked lists, trees, right? Graphs. So all of these data structures, if you observe, the size of these data structures can be increased or decreased as per the convenience during the execution of the program, or we can say at runtime. So runtime means when the program is actually executing, right? When the program is executing, you can change the memory size. So this is dynamic memory allocation, right? And all of these dynamic memory allocations happen from the heap section. This is a pool of memory that is specifically reserved for this purpose only. So this is why we have a heap section. So now let us take a example code, and by executing that code, let's understand how is the heap section used in the process address space. So let us see this example. So here you can see this is a simple piece of code written in the C language. Let us go over this code and understand what is happening here. So this is the main function, and the first thing that we are doing here is that we are asking the user to enter a number n, basically the number of elements, right? And this n is an integer and the user enters this, right? And then we have this function call which is called alloc. And when we go to this alloc, here we are passing the number n, the integer n, and then we are allocating a buffer. So here there is this dynamic memory allocation happening. So in order to do dynamic memory allocation in the C language, there are two function calls. One is malloc and the other is calloc, right? So what do you pass to malloc? So first of all, this malloc function is defined in the standard library header file, right? So what do you pass to the malloc function? So you pass the size of the memory that you want to be allocated. So As you can see here, we want the memory equivalent to the size of n integers to be allocated. So here you can see n into the size of int, right? We want this much memory to be allocated, n into the size of integer for n integers, and this returns a memory location, and we typecast it to a pointer, right? So buff is basically an integer pointer, right? It is basically pointing to an integer location, which is the uh, basically the pool of memory that we just allocated. It is pointing to the beginning of those n into basically the pool of memory that we just allocated, which has the size of n integers. This buff points to that, and this allocation will be happening on the heap section, as we'll see, right? So this returns this function alloc function returns the this address, the address of the buff, and it is stored in the this variable, another integer pointed, that is array, arr. Okay. So now what we are doing here is that now we are entering an integers, right? So now that the array pointer, let me call it array. Now that the array pointer is it is pointing to a integer, look, basically a pool of memory of n integers. It is asking the user to enter those n integers into this array, right? And finally it is printing all of those numbers, right? Simple program. Basically we are allocating a size for n integers, asking the user to enter it, and then printing it on the console. And finally, using this free function call, again this is a function call that is defined in the standard library header file, and using this free function call, we are deallocating the array, right? Basically those, that pool of memory, that pool of n integers that we just allocated for our array, we are deallocating it, right? We are returning it to the heap. When you take something from the heap, you must ensure that you are returning it, right? Otherwise it will cause a memory leak. So we'll talk about memory leak in this video in the next example. So now let us see how this piece of code will be executed. Basically we want to see how the process address space changes, how the heap section is used when this piece of code is executed. So let us start the execution of this piece of code. Here is the address space. We have the code section, data section. This is the heap section. Currently we have not allocated anything. And let's start the stack section by making a function call. So let's call the main function. So as you can see, this is the stack frame for the main function. And here there are three local variables, n, I, and array, right? So n is this integer where the user will enter the number of elements. I is this iterator. Basically, it is an index that we will use to iterate through the elements of the array. And finally, this arr will be an integer pointer. It will point to the pool of memory that we will be allocating, right? So let's see these instructions. So the first thing is that the user will be entering n, the number n, right? So here the user enters 100, right? The value of n is 100. And then we pass it to a function which is alloc, right? We make another function called alloc. So this is the alloc function. This is the stack frame for the alloc function, right? And here we have another local variable buff, right? So buff is an integer pointer just like arr. And here what is happening is that here we are making the library call to the malloc function. Here we will pass the amount of memory that we need. So for example, in this case, the value of n is 100, and let's assume that the size of integer in this machine is 4 bytes, right? The size of integer can be 2 bytes or 4 bytes, but let's assume that in this hypothetical machine, the size of integers is 4 bytes. So we are basically asking for a memory, we are asking for a dynamic memory of 400 bytes from the heap section, right? So when this malloc function returns, it will return a pool of memory, a buffer of memory, which is 400 bytes long. So let's see how it looks like. So when that happens, let's say, so an address will be returned, right? So let's say this is some address in hexadecimal format, 1f, right? So this is basically 0x1f is basically the address of the pool of memory that has been allocated on the heap section. So let us assume this is the buffer that we allocated, and it is of size 400 bytes, right? So here I have just taken a hypothetical example. Here the almost all of the size of the heap has been taken away, but that is not the point. Here basically this is the block of memory whose size is 400 bytes, whose address is some random address, let's say 1f, and this is the address that is returned by the malloc function, and this is what we stored in the buffer variable, right? Buff variable, right? So now we are going to return the buff variable, and that value will be stored in the arr variable, right? So now let's return from this function. So a very interesting thing is going to happen now. Basically something we should pay attention to. So when this alloc function returns, then this stack frame will be destroyed, right? This will be popped from the stack, and the value which is stored in the buff variable, that will be copied into the air variable. So this buff variable will no longer exist, but that does not mean that we will lose the handle to this block of memory. That address will be kept in air. So what I mean is that, so now that the alloc function has returned, so we do not have buff, but we still have that address, and that address is copied to air. And now the variable air points to the block of memory that we have reserved or allocated dynamically on the heap section, right? So this is the block of memory that we have allocated. Now let's see what is happening. After this alloc function returns, we are asking the user to enter those n numbers. So here the value of n is 100. So let's say the user enters some 100 numbers. So basically, let's say the user enters the numbers from 1 to 100 sequentially, right? So this is the input that the user has given, and as you can see, this input has gone to the heap section, this local this block of memory, right? It is not on the stack section, it is not on the data section, it is on the heap section. Although the pointer that is storing the address of this block of memory, that is on the stack frame, that is on the stack section, but the blob of memory, the buffer of memory, is in the heap section, right? And then what we do, we just print the contents of this block. So this numbers 1 to 100 will be printed on the console, right? After that, what we are doing, we are calling the free function, and in the free function you pass the address of the memory block which you want to free, which you want to deallocate, right? So as you can see, this is the block of memory that we just allocated, and now we are done with using it. Now we want to return it to the heap section. So basically, as we discussed, for dynamic memory allocation, the allocation and the deallocation is the responsibility of the programmer. They have to make explicit function calls to allocate and deallocate the memory, right? In order to explicitly allocate, we call the malloc function, which was defined in the standard library header file, right? In the same way, now it is the responsibility of the programmer to explicitly deallocate this piece of memory, right? Otherwise there will be a memory leak, which we will discuss about in the next example. So now when this free function is called with this address, this block of memory is deallocated. Now as you can see, that block of memory has been freed, and now again you can make further allocations on the heap section. So this is how you can make dynamic memory allocations on the heap section. So if you see, in this case, the size of the memory that we wanted, it was not known from before the runtime, right? So the user could have entered any value of n, right? It could be smaller than 100, it could have been bigger than 100. The point is that we do not know the value of n, right? The number of elements before runtime. So in that case, when we do not know the size of the memory that we want beforehand, we go for dynamic memory allocations, and that is why we have the heap section. So during the execution, while the program is being executed, we figure out, okay, we need 100 integers, and that is how we make a we make a demand for memory on the fly, right? So this is how the heap section is used. So now that we have understood how we use the heap section, we have a basic idea of the allocation, deallocation, right? All of this. So now let's talk about a very important concept which is related with the heap section, that is memory leaks. So now let us take an example and understand memory leaks, right? So as you can see here, we have a simple C program, and here we have two functions, main and alloc. So this alloc function is the same that we saw just a while ago. Here we are taking an integer n and allocating a buffer of size n integers, right? The buffer's size is equivalent to that of n integers, and we are making a call to the malloc function, which is, as we know, defined in the standard library header file, and this returns that buffer, right? An integer pointer to that buffer. Here we are taking a user input, that is, we are asking the user to input the integer n, and using that n, we are making three calls to the alloc function, right? So let us see how this piece of code behaves, and how does like what is memory leak, we'll understand with this piece of code, right? So let us start the execution. So here, as you can see, we have the address space, and let us call the main function. So as you can see, here is the stack frame for the main function, and let us assume that the user has given the number 10 as input, that is, the value of n is 10. Now we are going to call the alloc function 3 times with this value 10, right? So let us make the first function call to alloc. As you can see, the alloc function was called, and here we have this basically a memory buffer of size that is equivalent to that of 10 integers, right? Which is 40 bytes, right? Let's assume that the size of integer is 4 bytes in this machine. So this is a buffer of 40 bytes that is allocated, and the address, I'm assuming a random address in hexadecimal format, it is 0x1f, right? So the buff variable points to this piece of memory buffer. Now, what will happen? This buffer value will be copied to the array variable when the alloc function returns, right? So this is how the first function call looked like. Now let us make the second function call, right? Here, as you can see, we have made the second call to the alloc function, and here we can see the buffer, a new buffer has been allocated with the same value. That is, let's assume n is, and let's not assume, the value of n is obviously 10, right? So here, as you can see, the new buffer which is allocated here, again 10 integers, 40 bytes, and the address at which this is allocated is 2f, right? So now when the buffer, basically when the alloc function returns, right, and this address which is in the buffer variable will be returned to the array variable, and this value 1f will be overwritten. So here is where the interesting thing happens. When you overwrite the value 1f with 2f, let me do that for you. You see, we have lost the handle to the first buffer, right? We don't have any variable which is pointing to the first buffer, right? So in this case, this piece of memory buffer has been lost. We did not deallocate this piece of buffer, right? Which we should have done. As a programmer, it is not only your responsibility to explicitly allocate the memory on the heap, you also have to be careful enough and make sure that you are deallocating the piece of memory which you are allocating on the heap, right? So as you can see, here we had two buffers. Since 2f was used to override the value 1f, we lost this 1f handle, right? And this is an example of memory leak, right? So let's do this once again. Let's call the alloc function one more time, and the same thing will happen as you might have guessed. So the third buffer is allocated at the random address 3f. Again, it is 10 integers, 40 bytes, right? And the same thing will happen when the alloc function returns. The array value 2f will be overwritten and the new value will be 3f. And you can see we again lose the handle to the second memory buffer now, right? In the first function call, when it returned, no, when the second function call returned, we lost the handle to the first buffer, and similarly when the third function call returned, we have lost the handle to the second buffer, and now we have roughly 80 bytes of memory leak. So you cannot reuse these pieces of memory, right? Now these pieces of memory will be freed only when the program terminates, right? So if you keep on allocating memory and maybe you do not properly deallocate those pieces of memory, then those memories will get like they will be involved in memory leaks. That part of memory you cannot reuse to allocate to some other variable, right? So here we have to be very careful when we as a programmer are using the heap for dynamic memory allocations. You not only have to do the allocation, you have to also make sure that you are freeing the memory. So let's do the last statement of this piece of code. Here we have one free, we're calling the free one. So when that happens, the third buffer will be freed. So this one was fine, right? We allocated the third buffer and we freed it, right? So this one buffer we properly took care of, but the rest of the two buffers, since we did not call free, even if we call free at this moment, it will not uh, be meaningful, right? The current address is 3f. If we had two more function calls to free, they will not be, we cannot free these pieces of memory. You have to so the thing you can do is that we have to store these addresses to some other variable, right? We always should have the handle to in order to free these pieces of memory buffers, right? If we had stored the addresses 1f and 2f in some variables, then we could have freed this, but we overrode the value 1f and 2f, so now we have no way of freeing this piece of memory, right? So this was about the example of memory leaks, right? So guys, this was it for this video. In this video we understood why do we need the heap section, and through an example piece of code we understood how does the dynamic memory allocation happen on the heap. We saw the malloc and the free functions, right? And then we also talked about the memory leak, right? So as a programmer, you have to be careful while using the heap and make sure that you are deallocating the memory in a proper way, right? So guys, this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.